This video is going to take a look at the central limit theorem, which helps us find the probability the mean of a sample falls within a given range. Up until this point, we've dealt with finding the probability of one individual point. What's the probability one person is taller than 60 inches? Now we're going to collect a sample, find the mean of that sample, and compare the probability that mean behaves the way it does. The central limit theorem says if we have a normal distribution with a mean of mu and a standard deviation of sigma, and we took samples of size n, the mean of all the samples will be the same as the mean of the entire population. However, the standard deviation is going to be smaller because we're taking several data values and averaging them. We're less likely to get an extreme value for our mean because it's balanced out with all the other values. So we adjust the standard deviation of the samples to be sigma sub x bar, or the standard deviation of the samples, is the standard deviation of the population divided by the square root of the sample size. We can use this idea to find the z-score of the sample by doing a very similar formula as before, x bar minus mu divided by this new standard error, this sigma divided by the square root of n. And it turns out that if we have a sample size that's sufficiently large, in general larger than 30, these formulas will hold true not just for normal distributions, but any distribution. Any distribution with a large sample size will turn into a normal distribution with a mean equal to the same mean as the population and a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. So let's take a look at an example. In the US, the average man is 69.1 inches with a standard deviation of 2.9 inches. We're going to find the probability that one random man is taller than 72 inches. The key here is one random man. When we have one random man, we use our formulas that we used in the previous videos. We can just find that z is equal to x bar minus mu divided by the standard deviation, because we're just talking about one person. So the x value that we're interested in here is 72 inches, minus the mean of the population, which is 69.1, divided by the standard deviation of the population, which is 2.9, to give us our z value. So we can calculate that on our calculator, 72 minus 69.1. I always like to do it in two steps. Hit equals, divided by 2.9, and we end up with 1. If I were to draw a picture then of what we're talking about, we've got our normal distribution with the mean of 69.1. We're interested in 72. We want to be taller than that, so we're shading in the right tail. Using z-values, z-value of 0 at the middle and a z-value of 1.0 on the right, we're going to run either to our table or Excel to calculate the area that corresponds with 1.0. So we said that our z-value was equal to 1.0. To calculate our area on the standard normal curve, we'll hit equals norm.s for standard dot distribution. The z-value we want is 1, true, and we end up with an area of 0.8413. 0.8413 is our area, but remember Excel is going to give us the area to the left of our value. We want the area shaded on the right, which is going to be 1 minus 0.8413, which gives us a probability of 0.1587. Just over a 15% probability that one random man is going to be taller than 72 inches. If we change this, and instead of taking one man, we take a sample of 10 men, and we want to find that the average of those 10 men is taller than 72 inches. What this does is this changes the standard deviation. Now we have our standard error being equal to the old standard deviation, which is 2.9, divided by the square root of my sample size of the 10 men. So when we do on our calculator 2.9 divided by the square root of 10, we find our new standard deviation is 0.917. So now when we do the same exact process to calculate the z, we'll use our standard error instead of the standard deviation. Z is equal to x bar. The mean that we're looking for is 72, minus the mean of the population of 69.1, divided by the standard error, divided by the 0.917. And when we do that on our calculator, 72 minus 69.1, always doing two steps, 2.9 divided by 0.917, we end up with 3.16, a much larger z-value. And this is what's going to always happen when we have a sample, because everything is moved closer to the center, closer to the mean of 69.1. We want to have a mean of 72 or taller. We want to be in that tail. It's much the same picture, but now the z-values are different because the standard error is different. The z-value of 0 in the center and a z-value of 3.16 to the right. Let's go to Excel and find out how much area corresponds with 3.16. When we have a z-value of 3.16, we can say equals norm.s for standard.distribution. Type in the 3.16, true for cumulative, and that's going to give us 0.9992. So our area now is 0.9992. But remember again, that's always the area to the left. This problem's asking for the area to the right. So we'll do 1 minus 0.9992, which gives us 0.0008. Notice how different these two probabilities are. If we're just looking at one random man, we could have one random person that's taller than 72. Happens about 15 or 16% of the time. But if we take a sample of 10 random men and average them, the tall ones are averaged out with the short ones, and we're moved closer to the mean in the center, which means it's going to be less likely for us to be as far away from the mean. In fact, our probability drops from almost 16% to 0.08%. Very, very small. What if we extend it to a sample of 100 men? Now that we have 100 men, an even larger sample, it should be even rarer for this to occur. We have sigma sub x bar, or the standard error, is 2.9, the standard deviation, divided by the square root of the sample size, which is 100. That's going to give me a standard error of 0.29. And so now we take z is equal to the mean that we want of 72 minus the average of the population, 69.1, divided by our new standard error of 0.29. And notice how much larger that's going to make our z-value equal to. 72 minus 69.1 divided by 0.29. Now we have a z-value of 10.0. So if we make our little curve, the average is 69.1. We want to be taller than 72, which when we change that to z-values with a sample size of 100, gives us a z-value of 10.0, which if you're using the table is far off the table. We're using Excel equals norm.s.distribution of 10, comma, true. Even Excel says 1.0, or 100% of the area, is to the left of that point. So we end up with 1.0 to the left, which means to the right, 1 minus 1 is equal to 0. There's really virtually no area left to the right of that point, which means if we sample 100 men and average them, it's basically impossible to get an average of 72 inches if it's truly a random distribution. So this is the idea of the central limit theorem, is we find the probability that a mean of a sample falls within a given range. With the sample, we're keep the same average overall, but we push everything in closer to the center because the high values balance out the low values, making it more and more rare to get a sample that falls far away from the population mean.